Okay. So good morning and happy Tuesday. How's everybody doing? Yeah. Um, so I looked and only about eight of you have submitted project number two. Any questions about project number two? How's that going? Yeah. At a minimum, think of them in batches. If you can do depth first search, you can do breadth first search and uniform cost search, and throw in A-star search as well. So please, jump in. The water's fine. Again, you can submit as many times as you want. When you run it in the standalone auto grader, that's exactly the same tool that gets run on the back end GradeScope server environment. Only it runs it with the I think it's the dash auto grader output, which should generate some JSON stuff that's parsed and sliced and presented in other databases. Okay, so the plan today is to go over heuristic design, some ideas that are important for rounding out your understanding of uninformed search and informed search. And then we'll slowly pivot the class to probabilistic concerns with expectamax and min-max search to support multi-agent considerations. And that'll lead us ultimately into some Bayesian approaches and some reinforcement learning, which is where we'll end the course. Okay. But before we begin, the usual administrative bits, the reading has changed. Section 3.6. I did recalc the syllabus. I threw in a couple sections from chapter 4. It's important to things that we'll be getting into when we pivot to reinforcement learning. So there's a new revision, version 1.12 of the syllabus on the Canvas site. And I'm also going to update the slides. When I looked at the slides this morning, today's slides, there were some spurious artifacts that weren't there when I saved it yesterday. So I'm not sure what the PDF looks like. I just assume PowerPoint for Mac does the right thing, which it doesn't always do the right thing. So you can expect an update on the slides right after this. Office hours will be today from 10:30 to 12:30. I'm going to hold them in my lab, which is 105, the robot lab. So please feel free to come by. If 10:30 to 12:30 doesn't fit your schedule, please, shoot me a Slack message, and I'm more than happy to arrange a mutually agreeable time to help you. And so there's a big chairs meeting on Wednesday that I have to get to. So, and I have to do some pre-prep for that. And there's some other administrative stuff that I have to attend to. But certainly, please reach out early, not the last minute, if you have questions. Also, for questions about the course and the project, I strongly encourage you to pose those on the course Slack channel. I promise you that at least a third to a half of your colleagues in the class had the same question. And that helps me to so-called force multiply for other people when they see or benefit from that interaction. Okay? All right. Any questions? Oh, homework number one will be released today. Homework number one will have two components. Well, there are two versions, one for the undergrads and one for the grad students. I'm tying up some loose ends for the graduate student version, but I will reinforce things that you're doing for project number two. Okay, so it'll be some hand calculations based on different types of searches. Okay, any questions? Things. And this time I made sure not to put the answer in the slides I posted, right? Um, so, and of course, I took German for 7 years. And at one point, I could speak and understand German, but that was decades ago. So, never got a chance to practice it. But the country of Switzerland, what is the best part, do you think, about living in Switzerland? Or was ist das Schönste am Leben in der Schweiz, right? What's the best part about living in Switzerland? What do you think? What do you think? They're known for a lot of things. Yes, Amici? Oh God, really? You heard this before? Oh, come on. All right. Yes. I don't know. But the flag is a big plus. I thought it was funny. All right. Oh, thank you, Amici. All right. So the question of the day I have for you to get those cognitive juices flowing. Um, oops, I'm hearing something in my ear. I'm hearing a Pac-Man death sound in my ear, which shouldn't happen. Um, all right. So the question of the day. We present here a basic Pac-Man maze, and thinking about how you define state is an important exercise that monitors off in the right. Um, so let me ask you, for this version of the Pac-Man maze environment or Pac-Man game, what considerations, what would you reflect as this idea? Thank you, Nikki. As this idea of state. How would you define state for this particular problem? What do you need? What pieces of information are important? Yes, Nikki? Okay. So Pac-Man's position and pellets that have not been eaten or eaten. So do you have two lists of pellets? Okay. So you have one list, and that list in each position reflects whether or not a pellet has been eaten through a Boolean. Okay, great. And so let me ask you, what's the goal state look like for this particular environment? Anyone? What's the goal state? Oh gosh, don't tell me. I don't know. I'm sorry. I'm sorry. Anthony? Antonio. Oh, it's close. There's an approximation. It's not right though. Antonio. Antonio. All pellets are eaten. Does the Pac-Man position portion matter to that goal state? Okay, so let's explore that. Why would it yes, and why might it not no? Hmm. Hmm. I see. And so by the sheer nature of pellets all being eaten, Pac-Man's position would most likely be one of those pellets, that last pellet. But the position itself isn't important to the definition of the goal state. Great. Okay. So how about this environment? So we're going to introduce some other stuff. What considerations, in your opinion, hear your thoughts, would you include in the definition of state for this version of the Pac-Man problem? Hear your thoughts? No? Put yourself out there. Oh, man. Could you tell me your name? See, that's Antonio. And you're Alex. Alex. Okay. And the power pellets. Why the position of the ghosts? Ah, that sound of Pac-Man death that played in my ear. Absolutely. And so here we see as Alex and Tony. Okay. As Alex said, um, the ghosts matter, their positions, because that impacts this idea of what goal is, right? If Pac-Man goes away, you'll never reach that goal state of having everything consumed. But let me ask you, follow on, and this is open for everybody. If the Pac-Man position coincides with the ghost, is that always a bad thing? When is it not a bad thing? When might it not be a bad thing? Alexander? After Ah, after eating one of the big pellets. So after eating one of the big pellets, and I had to look this up, the ghosts are scared. This is after decades of Pac-Man playing. The ghosts are scared, and it's actually a good thing if Pac-Man's position coincides with the position of a ghost, right? And so while that aspect matters, our goal state ultimately should be that everything is eaten, right? And so when you define state, you need to encode all of the relevant aspects of observations that you can make about your environment that is necessary to be able to act, but also to advance upon some notion of a goal configuration or goal state. Okay? All right. Now, for something like Pac-Man, okay, there are a lot of moving pieces, and the maze can get big, and you can have variations of the game. But certainly for other things, particularly for physical mechanisms like mobile manipulators, robots, you have to really think hard about what this idea of relevant aspects of the environment are, right? And so in any sort of practical AI implementation, you're going to spend a considerable amount of time looking at definitions of your environment. Now, of course, for environments like the maze, things are discrete. But when you add partial observability and non-determinism, it gets more and more difficult to represent notions of state. Okay. So that's just to say, yes, this is a defined environment, but you still invest and make the time needed in order to define this notion of relevant aspects of your environment as expressed by your state. Okay. Any questions? No? No questions? No? Hopefully this isn't the quiet day like last time. Okay, so let's take a look at heuristic functions. And we'll refer to the eight puzzle. And I'm so paranoid about the sound going out. Okay, we'll refer back to the eight puzzle, and a lot of this module refers to the eight puzzle. It's based on section 3.6 of the book. The eight puzzle is depicted here, and it's a game. You have a bunch of tiles, and these tiles are numbered one through eight, and you also have a blank space. And these tiles can slide east, west, north, and south. And the goal is to arrange the tiles in some numerical order. Now, I grew up on eight puzzle, among other things, and I'm going to go by what the book says, not by what I know. But from the eight puzzle that I grew up on, it was always assumed that the blank space was in the middle, three, four, five, six, seven, eight, and not in the upper left-hand corner. But I'm going to go with the standard for the book. I don't know if you're familiar or you know or use the eight puzzle, but I'm going to go with the standard for the book just to kind of reinforce what's there. And so the goal state is on the right here, and we see the tiles are arranged in numerical order, top to bottom, left to right. And when you talk about the arrangement of the tiles in numerical order, they ignore the blank space, right? So honestly, it really doesn't matter where the blank is, but just for consistency's sake, I'm going to go with the blank in the upper left-hand corner. And so when we think about this state space, the first question, and I'll put out this question to you. So in my mind, I'm going over Antonio. Oh, crap. Don't tell me. I just blanked on your name. Alex, Antonio and Alex. Um, how do we count the size of this state space if we were to depict or think about or describe this state space? How are we going to count it? How big is this state space? Hear your thoughts. Nikki? Mm-hmm. It'd be 9 factorial. Okay. So we have our state space. and we can arrange them and think about them in some order, and it doesn't matter where the blank is. So we have 9 factorially many arrangements. Okay. But for which is this number, 362,880. Now that seems pretty big, but when we go to the 15 puzzle, it gets even bigger. It's like a couple trillion, right? Like 10 trillion roughly. But the other less intuitive part has to do with constraints, i.e., the structure of this particular problem that modifies our notion of the size of the state space. But absolutely, we start with 9 factorial. Now, if we consider the tiles in row major order, not paying attention to the blank, let's make a few definitions. There's this notion of a so-called inversion. And the inversion is related to this idea of this row major order, the numerical order of the tiles in sequence. Okay. And so an inversion is a pair of tiles. Let's say tile I, where I is the numerical value and J is the numerical value, such that I appears before J, but I is greater than J, i.e., the tiles are out of order, out of their numerical order. And so with this idea of inversion, we're going to look at this state space, this pool of 9 factorially many configurations in order to properly count the size of the state space. Okay. Any questions? Antonio and Alex. Okay, I'm burning that into memory. So this idea called parity. Parity is the number of inversions that you have in an ordering of the tiles for any particular configuration of the 8 puzzle game. And this inversion can either count the number of out of order tiles being even, or this out of orderness, you could call it, being odd. So let's see an example of what an inversion is. So imagine we have this sequence, 1 through 8, followed by blank, and for the numerical order, you take out the blank. You just don't even consider it. Blank doesn't matter. And so we have 1, 2, 3, 4, 6, 5, 7, 8. In this case, the 6 is to the left. It precedes the 5, but its numerical value is greater than the 5. There's only a single such inversion in this sequence, and so we say this particular sequence, 1, 2, 3, 4, 6, 5, 7, 8, has so-called odd parity. Does that make sense? Any questions? No? All right. And so the action that you can play are admissible actions. You can swap a number with the blank. And so the structure of this particular state space, it kind of limits you among the 9 factorially many states that you count. And here's why. Every time you move, each move preserves parity. So that means if you have a configuration that has odd parity, any move you make will produce a configuration that also has odd parity or reachable state. Likewise, if you have an even parity, any move that you make is always on another state that has even parity. So that means that even parity configurations only reach even parity configurations, and odd parity configurations only reach odd parity configurations. So I don't believe you on this. Well, try it out for yourself, right? So let's imagine this start state we have on the left, 7, 2, 4, 5, 6, 8, 3, 1 in row major order. Okay. If we count the inversions, we start with the 7. So we have 7, 2, 7, 4, 7, 5, 7, 6, and 7, 3. Okay. 7, 1. Then we have the next one, 2, 1. Okay. There's only a single inversion. For the 4, we have 4, 3, 4, 1, 5, 3, etc. And so if you enumerate all the inversions in this particular configuration, you count 16 inversions, so it's even parity. right? Okay. So now let's go ahead and let's move the two down, right? So this two is going to come down. Oh, that's a bad color. This two is going to come down into that space, and I'll just draw the two here, leaving a blank here. So the two is going to swap positions with the blank, okay? And so we result in a sequence seven, row major, seven, four, five, two, six, eight, three, one. If we count those inversions, we have 7, 4, 7, 5, 7, 2, 7, 6, 7, 3, 7, 1, 4, 2. Oh, 4, 3 is not, yes, 4, 4, 2, 4, 3, 4, 1, etc. Right? If we count all the inversions for that resulting state, that successor, as a result of that action of moving two down, or we could say equally well, swapping the two with the blank, now you have 18 inversions, right? We have even parity. And so with this, you always preserve parity for every single move. Said differently, all of the successor states for any node that you expand are also going to preserve parity. So if you think about it, that almost looks like closure property, right? If you said, I have this set of integers, um, the set of integers is so-called closed under addition, right? The resulting outcome is also within that set. But the set of integers is not closed under division, right? And so you can think of this idea of preservation of parity as a kind of notion of taking an operation or computing something, doing something, or executing a function, as it were, and it maintains parity closure. Okay, so every move preserves parity, i.e., even parity configuration or state reaches even parity, odd parity reaches odd parity. So this has the effect of partitioning your state space into two groups. And so, yes, we count the 9 factorially many configurations, but depending on what configuration you start in, if it's an even parity or an odd parity, you are going to preserve parity. So you only have available to you half of that 9 factorially many states that you count, raw states. Does that make sense? Any questions? So this is, if you've taken abstract algebra, this is kind of like a group. And the reason why you study properties like this is because you're looking at the geometry of algebraic constructs to try to find properties like, is there symmetry? Because once you can recognize things like that, you can compress your search and exploit all sorts of tools or make use of all sorts of tools to make problem solving easier. And there is, or was, when I was in grad school, a body of work being done in reinforcement learning for navigation for finding symmetry in navigation environments and on navigation problems. Because if you can find symmetries, you can have more compact summaries of your state space, which gives you a savings when you're trying to do search in non-trivial environments. Okay. All right. Any questions? No? All right. So, and this is just the definition of a group. I'm not a topologist, so you'd have to talk to somebody in the math department if you'd like to know more about that. All right. So the 15 puzzle has over 10 trillion states. It still preserves this idea of closure in terms of the parity, right? Under these actions. But as you can see, you go from the 8 puzzle to the 15 puzzle, and your state space absolutely explodes in size, right? So just for something as trivial, seemingly, as this puzzle game, you can have environments that you can't really solve in a modern day computer. Okay, not easily. Okay, any questions? No. So it's important then to kind of tie this to what we had at the outset for the question of the day. It's important to include only notional relevant aspects of your environment in your description of the state space. Moreover, when you enumerate your state space, there are opportunities to effectively compress your representation, and compressing your representation can help you in your problem solving. But sometimes you just can't get around the size and scope of the problem, and you have to tinker with your informed search or your uninformed search in order to get it to fit in memory or to reasonably complete in some amount of time. Okay, that is desirable in terms of time being the number of nodes that are expanded. Okay. Any questions? No? All right. So let's consider two different heuristics. And this is all in the book. And one heuristic we'll call heuristic one is going to count the number of tiles that are out of position in numerical order. The other heuristic we're going to consider, heuristic two, is going to measure the sum of distances, the Manhattan distance of the tile, each tile from their goal position. And so the example given, H2, for the starting state on the left-hand side, if we take the 7 should be down here on the goal state. We're going to go down 1, 2, and then um, 3 positions we're going to move. And so this movement is either north, south, east, or west movements. And so the 7 Manhattan distance is 3. The 2 Manhattan distance, it's going to be 1 because the 2 comes to rest in the goal position here, 1 position to the east. Okay. Does that make sense? All right. So the example here, Manhattan distance of the start state is going to be a total of 18. So we have two different heuristics, and one of these heuristics, well, they're equally usable heuristics. They're both admissible. They're underestimates of the distance of the goal. But you might ask, well, what might or might not make a heuristic better than another, right? It's an important consideration. What does better mean? And what is the impact of this notion of a better heuristic, keeping in mind that a heuristic has to be admissible and in the best case satisfies the triangle inequality. It's consistent. Okay. Any questions? No, no questions. So let's take a look at considerations for accuracy and performance. And this is the slide where I have no idea what PowerPoint for Mac was doing. It just had some stuff that I never used. I had cut it and pasted it and then cut it and decided to go with a drawing instead of an image. And it, for some reason, the image was still there on what I had, but not when I saved it. But nonetheless, there's this notion of an effective branching factor. And so this figure is an illustration of just a typical set of tries for node expansion. And our branching factor B is the number of successors or upper bound on number of successors that you have for any expansion. And so our effective branching factor makes an assumption that your number of children is constant for each node, which isn't the case in reality for many environments. But for the case of analysis, we assume that it's constant. And so imagine we have some depth D, and if we're going to count all of the nodes expanded, well, it's the sum 1 plus b squared up to b to the d power. Okay. And so our effective branching factor, B star, is defined as follows. Imagine you're doing a heuristic search, A star search, f of n equals g of n, or path cost, plus h of n, our heuristic, our estimate to the goal. And let's imagine you generated n many nodes at solution depth d. Your effective branching factor, B star, is the solution to the following equation. N plus 1 equals that sum involving B star. And so your effective branching factor, which is not the same as your branching factor, is the solution of that B star that satisfies this equation for N plus 1. Does that make sense? Any questions? No? All right. And so an example, if n is 52 and the depth is 5, your effective branching factor is 1.92. Now, of course, you'll notice that effective branching factor can have a fractional component, right? It's not the same as branching factor. It's an analysis that talks about how effective heuristic search methods are. And so a better effective branching factor, B star, is going to be a value that's closer to one, right? If it's exactly one, that's the best case, which almost never happens. But it gives you a benchmark to say how good is one heuristic relative to another heuristic. And this is both in the theoretical case and it also plays out in the empirical case if you try a couple of different methods. Okay? All right. Any questions? No? And so it's known that A star searches, they prune. And as we saw, because of this performance evaluation, f of n equals h of n plus g of n, there are certain subtrees in our state space that are pursued before other subtrees. And because of that, this idea of considering one subtree in your graph versus another, it's thought of as pruning, right? You're eliminating from consideration. Okay. So effectively, what happens is this pruning action reduces the effective depth of the tree. You're not going down everywhere. You're only going and pursuing some places. This gives you a multiplicative improvement or reduction, if as it were, a big O of B to the D minus that reduction versus big O of B to the D that you'd get in something like breadth first search. Okay. Any questions? No. So let's take a look at our two heuristics. And I had to make this small because there's a table from the book that I wanted to put below it. We have our H1, which is the number of misplaced tiles. And let me ask you, is H1 an admissible heuristic? What's your opinion? Is H1 the number of misplaced tiles? Is that admissible? You count one for every tile that's not in the right order. What do you think? Share your thoughts. Nikki? Okay. So let's go back to what admissibility means. What does admissibility mean? It's an Chris? Correct. Correct. Or to use positive logic, you say it's underestimating. It can never be more than the real length, cost of the goal, but it's always less, right? And the navigation example, we said Cartesian distance is an underestimate. And it's an underestimate because roadways are not straight, right? They curve and they fold and they turn. So by that definition, so let's ask again, is H1 admissible? Why? But let's kind of peel back the layers of the onion even more. Why is it not overestimating? Why is it not? And there's a hint. It only counts one for each tile. Chris? Mm-hmm. 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 Yes. And if a tile is in place, what does H1 do if a tile is in place? It's already in the right place. It doesn't count it. It says zero. If a tile is one move out of place, what does H1 say for it? It says one. Alex. All right, there we go. I had to go through my database of bases. If a tile is two moves out of place, What does H1 answer for it? One, Amici. If it's three out of place, what does it answer? Answers one. So in every case, H1 says, I don't care how many moves out of place you are, I'm only going to count one. So you're either in place, count zero, that's an exact estimate, or you're out of place. And it doesn't matter how many you're out of place, how many moves, it always counts one. So it's always less than or equal to what the true number of moves are to put something in place. So it's always an underestimate, and therefore it's admissible. Does that make sense? Okay, so I really want to walk you through considerations of this idea of admissibility. All right, so then H2, is H2 an admissible heuristic? So what are your thoughts? Let's hear if you could share your thoughts, please. Chris, right? Okay. Why is it admissible? That's true. You're answering the question, right? Why is it admissible? Hmm. Because it respects exactly how things move. So if it says the distance to put it in its correct place, that distance is always counting moves down or up or left and right. Okay, so it is admissible. Okay. So at this juncture, let me ask you, which in your intuition might be better as a heuristic, H1 or H2? Tenzin? Hmm. I see. So one is kind of general, let's say, so you're far or you're close, but the other looks more like the number of steps you need to take in order to put it in its correct location. Okay. All right. So figure 3.6 in the book runs a bunch of searches, including A star with the H1 heuristic and A star with the H2 heuristic. And some of the things it lists is the depth and the number of nodes generated. And if we take a look at breadth first search, BFS, relative to A star with the H1 heuristic, we see that A star with the H1 heuristic, it significantly prunes the number of nodes under consideration as we expand the frontier. We look at A star with the H2 heuristic. It also significantly prunes the number of nodes considered, and it does more so than A star with the H1 heuristic. Okay, so let's turn our attention to the right-hand half of this figure table, the effective branching factor. It solves that equation, n plus 1 is equal to that sum associated with the nodes expanded, assuming a BFS type expansion. So when we solve for B star, we see that BFS for the effective branching factor, as the depth increases, yeah, it gets better. But both A stars, A star with the H1 heuristic, A star with the H2 heuristic, the effective branching factor is better. It's closer to one. Moreover, H2 beats H1 in terms of the effective branching factor. And we can see that this is preserved as the depth gets bigger. A star H2 version beats by effective branching factor A star H1 version. Okay, does that make sense? Any questions? No? And so if you look at the value of the heuristic, now this is not the effective branching factor. I'm talking about the value here in red. For all nodes that you consider in the state space, A star, the H2 heuristic, is always at least the H1 heuristic. And we know this because, as we just discussed, the H1 heuristic always returns one. But the H2 heuristic returns the number of steps that you take in order to position that tile in its configuration in the goal state. Okay. And so when this happens for every single node, we say that H2 so-called dominates H1, right? In the best case, it's the same, but in most of the cases, it's different. It's the same only when the tile is one move out of place, but it's bigger if the tile is more than one move out of place. Does that make sense? Any questions? No? All right. And so when we think about this idea of a heuristic dominating, we think back to this idea of weighted A star search. And we said when you weight the heuristic, that heuristic is taking your contour, your search contour, and projecting it out towards the goal at a much faster rate than if your heuristic had a smaller weight. So in effect, this idea of dominating H2 dominating H1, it means that the contour associated with f of n equals g of n plus h of n for the H2 heuristic is going to push its contour out towards the goal at a faster rate. And so with H2 as our heuristic, it never expands more nodes than H1. They still have, because they're admissible, the same optimal solution cost. But you could think of, and I'm trying to use a traveling analogy, H2 gets there faster, right? Taken differently, H1 explores more nodes. We see with domination, H2 in some cases is exactly equal to H1, right? But in most of the cases, it's going to be bigger, and that bigger means your contour is going to grow out faster. So you're going to approach your goal at a much fewer number of expansions. Does that make sense? Any questions? No? All right. And so let's think about this, and this part is actually in the book. If your heuristic f of n is h of n plus g of n, and we said that this A star search, i.e. your heuristic, results in an optimal solution path cost. We call that C star. So everything that's less than C star is going to want to explore those nodes, and everything that's exactly equal to C star, we call that the goal contour, right? Your goal certainly exists on the goal contour, but you might have a couple other nodes that are also on the goal contour. And so if we do a little bit of algebra, we have h of n is less than c star minus g of n. Well, the actual path cost, that's the same for both of them, right? The difference is that gap between c star and that actual path cost that you accumulate as you take steps, as you expand the frontier. I keep saying frontier. So if we know that h of n, h2 of n, our H2 heuristic dominates your H1 heuristic, that means within your optimal solution cost path, it's going to at least explore, in the worst case, the same number of nodes as H1. But because it's bigger, well, it's going to push that contour forward at a much more dramatic, faster rate. So your H1 ends up searching more nodes than your H2, right? Does that make sense? Any questions? So higher H values for admissible heuristics, if you have a choice, are typically better for this reason, and this reason is domination. Does that make sense? All right. So another approach that you can take, and this is also in the book, when you think about and when you design heuristics, is this idea of solving a relaxed problem. And I know we just got done saying, well, what aspects of the environment are important, but relaxations can sometimes be useful for creation of heuristics. And so in the eight puzzle, we know that the tiles can only move north, south, east, or west. Well, one relaxation could be a weird tile world where it could move in any direction, even along the diagonals. I mean, how are you going to implement that, right? That's just not how 8 tile works. But as an exercise, if the tile can move anywhere, then using H1, this idea of out of place, it can give you the shortest solution, right? And so sometimes, not all the time, but sometimes when you relax the constraints on a problem, um, and more impoverished heuristic can sometimes give you optimal solutions. Does that make sense? Now, of course, when you actually try it out, you have to try it out on the actual game. But this is just coming up with a heuristic that can find solutions. You run the simulation, you have your heuristic function, and then you use it as an evaluation in the actual version of the environment. Does that make sense? All right. And so you can often use relaxed problems to arrive upon solutions that you then apply in the fully constrained problem. Moreover, you could have a suite of heuristics. So let's say you had H1, you had H2, you have a couple of others. Maybe there's a Cartesian distance heuristic. Maybe there are, a whole host of heuristics. You could have a heuristic that selects the best prevailing heuristic at the time. Comp is a weird kind of function, right? Um, Now, you have to assume if you take an approach like this, yeah, that's going for maximum domination. If this notion of a greater or better heuristic arises from one round to the next, you just pick that one. And then maybe the one you pick might change depending on what part of the state space you're in. But the only assumption here for something like this approach is that each of the component heuristics have to be admissible and or consistent, where consistency, triangle inequality, is the stronger property. Does that make sense? So that's just saying a heuristic that is a composition of a bunch of heuristics is admissible, provided that the component heuristics are also admissible and or consistent. Does that make sense? All right. So you can imagine something like your Pac-Man game. One heuristic might say something like, let me think about my distance from the ghosts. If I want to take a move, I look at expansions and I consider what's going to keep me further away from the ghosts. Then you might have another heuristic that says, how close am I to the closest food pellet? Because consuming food pellets is a good thing in the Pac-Man game. You might have another heuristic that says, how close am I to the nearest power pellet? Because power pellets free you from having to care about the position of the ghosts. You eat a power pellet and you can go anywhere for some period of time. And so if you had all those heuristics in play, um, yeah, they can advance you to your goal state. And you can do the analysis to determine if they're admissible. But which one do you choose at what time, right? Because this idea of one heuristic versus another heuristic, at some point, one of the heuristics might light up as better. At other points, it might drop out. Okay. All right. Any questions? No? All right. So another way you can solve complex environments is to have what are called landmarks. And these landmarks are goals, or rather are states, not goals, that you believe will lead you towards your destination. Now, as I understand from people who have Tesla products, when you use the GPS, one of the things it will do, like you're on a road trip, is it will plan your route assuming calculations for battery power, and it will plan stops along the way. Not plan, it'll take you through routes on paths that include charging stations based on the calculation of how much range you have left. And in essence, you can think of those as a kind of landmark, right? They're these states, in case of navigation, they're locations on the map that will lead you towards a solution. But one of the things you can do then is that if you can identify these landmarks that are in your state space, there's some states that you say, I'm going to make this a waypoint. Now you can pre-compute the solution from those landmarks to the goal, and then the problem becomes one of finding the quote unquote right landmark. Okay. So in this case, the example given, and this is in the book, imagine that we have the following problem. blank 1, 2, 3, 4. Now, of course, that doesn't include 5 through 8 tiles. It doesn't matter. This is a quote unquote subproblem. So if you identify the subproblem, you can then compute a solution from this particular subproblem to the goal. And the goal means finding moves or paths that get the other tiles in their rightful place. Now, when you're faced with a new configuration starting state, it's just a matter of planning your path to get to the subproblems. And so what this does, it has the effect of reducing your search. And the key consideration is where is the landmark relative to the goal? And is this landmark on the optimal solution path? But this can be useful because in pre-computing the distance or the path or solution from these landmarks to the goal, you're sort of saving the number of nodes that you expand, and you're saving the amount of space that you're going to need to do a from scratch informed or uninformed search. Okay. Any questions? No? So let's take a look at our complexity. Imagine if we had these five values, blank 1, 2, 3, 4. The complexity of this state space is you're taking arrangements of 5 out of the total 9 that you have, which is roughly over 15,000 different states. And if you think about those 15,000, roughly 15,000 states, that's a much lower complexity, 10x lower complexity than the complexity of the full state space of the 8 puzzle problem. And if you go to the 15 puzzle problem, a reduction like this gives you about 1,000 fold reduction for that 15 puzzle. And so the idea then is rather than uncovering solution paths from scratch, you choose a subproblem, compute the solution path for those subproblems, which is a smaller number of states, and then it's just a matter of finding a path to those landmarks. Does that make sense? All right. And so you can have arbitrary sequences of subproblems, and it's just a matter of caching away those solutions to those subproblems, which are smaller than the full state space. And now you pay the cost of finding a path to the subproblem, which results ultimately in a savings. And so your new heuristic would essentially be your heuristic that checks the database of subproblems. And the worst case is going to be the pre-computation of these solution paths from your reduced size state space of subproblems. So you build your database is reusable, and now you're just trying to find a landmark that you've cached away in your database. Does that make sense? Okay. And so let's look at this idea of landmarks. And in the book, they use a navigation example just because it's easy to register before going to something like a Pac-Man or an N Queens or backgammon and stuff like that. So you cache your optimal paths, and you could, if you wanted to, pre-compute optimal paths for all pairs of vertices. But you're not going to do practically all pairs of vertices because for large complex state spaces, you're going to spend too much time doing that. But nonetheless, the burden on space is order v squared, magnitude v squared. V is a database of states. And for your time, you pay the cost of some shortest path algorithm. Right? And there are lots of them, Floyd-Warshall, there's Dijkstra, all sorts of algorithms you could use to compute shortest paths between nodes. Okay. And so the compromise then, given the size of your state space, because we saw that the 15 puzzle has like trillions of states, right? Maybe you choose some fixed number. So this is order O, big O of 1, some fixed number of landmarks. And then the question becomes, where do you place this budget of landmarks throughout your space? And then once you pre-compute or select this set of landmarks, you find the shortest path between any vertex or state and the pre-computed set of landmarks. And then your heuristic then becomes the cost optimal of getting from any node, any state, to that fixed set of landmarks and from that landmark to the goal, which you have when you pre-compute. Does that make sense? So there are lots of strategies you can use to place these landmarks. And these landmarks, let's see, I just kind of said this, the shortest path between a vertex and the landmark. Okay. And then, all right, so I had an illustration. I forgot about this graph. So you can pre-compute a set of landmarks and imagine then if this node is the state where you are, and I should have made these other colors, and these other nodes or states, locations in this case, are your landmarks. So then you look at the shortest path between your node where you are, your state, and each of this fixed set of landmarks that you did in big O1 time. And then after that, you take the path from the landmark chosen to the goal. So you're basically minimizing the cost of two things, that distance from your state to some landmark, and then the cost from that landmark to the goal. Now, the next question then is how do I place these landmarks? If I have a state space that's 181,000 or a couple trillion states, and I have this budget of 20 or 100 or 1,000 landmarks, how do I place these landmarks? That's an important consideration because poor placement will mean you're going to really be off and not get good solutions. Good placement means, okay, it might not be optimal, but it's good enough because it's tractable, right? And so this another concept of this notion of shortcuts, right? And a shortcut, just as the name implies, it's a cut through, and we see that on the side streets here of Worcester, right? Um, you have a pathway to get from a node to a successor to its successor. If you know that that's on an optimal path, then you can cache away a database of multi-action, multi-step actions and associate a cost with that and just take it directly rather than uncovering it from scratch each time. This is efficient, but it's not admissible because if you're using landmarks to do this, you might overshoot your goal. And then the cost, additional cost it takes to get back to the goal from an overshoot is going to be a suboptimal solution. Okay. All right. So this is called a notional differential heuristic. And it's called differential because the cost to your landmark might not be the same as your goal, and you're going to have to incur additional cost to get to that goal. And so placement of landmark is really, really important consideration because your goal might be on an optimal path to a landmark. So in going to the landmark, you're already getting part of the way on what's the optimal solution path. That's the best case. But it could be that your goal is outside of the optimal path to a landmark. That's not very useful because you're going to have to wander back to that optimal solution path, and that additional set of steps is going to cost you, right? And we're after optimality at the end of the day. So, selecting landmarks, there are a number of ways that they discuss in the book, and these certainly aren't exhaustive. You could just randomly select landmarks. You take your state space and you flip a multivariate coin, so to speak, and then you just arrive upon a number of states. You call them your landmark. Okay, that could work. It might not work. And it needs to be repeatable. It's not terribly repeatable. Another approach you could try is I'm going to go for coverage in state space. This notion, and I like to visualize it on a map because it makes it understandable, is you have some idea of a regular partitioning of your state space, and then you choose points or states that are at some placement in that regular partitioning. So that gives you coverage if, for example, your goal, I'll use gold here. Is that, no, that doesn't show up well. Let me use something darker like purple. If your goal is here, well, there's something nearby for some definition of nearby. If your goal is down here, Well, there's something nearby. Well, these two versus the one over here. If there's something here, well, yeah, but your goal in this case, with this regular partitioning, this coverage-based argument, your goal is going to be always some distance. You could say in this example, half the distance between two closest landmarks away from the goal, right? In the worst case. Okay. That might be reasonable for some problems. Okay. So you could also go for perimeter. You want to put the landmarks out further away on the graph with the idea that maybe the goal is out at the boundaries of your state space, which is not always true. In that case, you'd identify a notion of a centroid of your state space graph, and then you partition your graph, and this is the best visualization I could come up with of my own accord, and then you compute a notion of a selection of a state that's some maximal distance away from the centroid. And this gives you coverage, like we saw with the regular partitioning, but it also puts them equidistant between the center of the graph and the exterior of the graph. And like we saw at the regular partitioning, if your goal is in here, well, you have a maximum solution cost that you could expend trying to find the goal. If your goal is out here, well, that's a good thing. And you have coverage regardless of what part of your state space the goal is in. These are far from exhaustive list of how you would place your landmarks, but placing a fixed number of landmarks means you have to make a choice. And you want to make sure that this difference in your differential cost is not going to be too bad. And in many cases, you can almost upper bound what that cost is should your landmark be outside of the goal or beyond the goal, or you overshoot your goal. Does that make sense? All right. Any questions? No? I think this might be my last slide. Yeah. Nope, not. But wait, there's more. Forgot about this slide. Then you can have a learning-based approach. And with a learning-based approach, yeah, it works for complex state spaces. You start out and you just generate many starting configurations, just sample from it. So it's a simulation. Then you find a solution path, and then you cache these pairs, the goal um, and the path. I should be cost in the path, not goal. But nonetheless, you have this database of example solutions from arbitrary states. And because you've sampled from it randomly, the hope is that provided your state space is not too big, you have enough samples to give good coverage of different locations in your state space. So once you collect all of this data, now you design some features. And these features might measure different aspects given the goal and the path, different aspects of these solutions. For example, you might say the one feature in the case of 8 puzzle might measure the length of consecutive sequences of numbers, 5, 6, 7, 2, 3, 4, right? That might be one aspect of a feature or some statistic or something you measure about a node. Or in the Pac-Man problem, a feature might be the distance to the closest ghost, right? Because distance to closest ghost might be an important descriptor or aspects of a state when you have a bunch of solutions from randomly generated start states. And so with that, then you run a learning problem. You try to find a heuristic that is some weight. This is kind of a regression problem. It is a regression problem, but that's not the only learning approach you can have. You can have decision trees, random forest, you can have all sorts of things. But the idea then is you generate a bunch of experience. That experience is starting states and their solutions. You design descriptors over that database of solutions, and then you learn what is the right combination associated with this database of experience that you have in order to arrive upon a suitable heuristic. Now, of course, the cost that you pay for this, no pun intended, the cost that you pay for this is in all of this solution finding that you have for these randomly generated states. And the trade-off is how many randomly generated states, how much experience do you generate, and solving and then training this learning problem in order to get good learned heuristics. And there's no one recipe. There's some trade-offs here between time and memory and so forth. But in this case, you're using things that are important to the problem as your game proceeds in time because you're looking at experience from various scenarios. And so one of these sampled configurations might be what you see here in Pac-Man. Another might be the Pac-Man is way over here from next to the pellet, close to the power pellet, but very far from the ghosts. Another might be it's just out in space consuming pellets, right? All sorts of different scenarios for the experience. What is important from each type of part of the state space for defining a notion of the cost to the goal. Does that make sense? All right, now, this is a very data intensive approach. And for something like the large maze or the 15 puzzle, you're going to spend a lot of practical time and computation. But it does work. And the burden is designing good features. What aspects of the problem do you think are important? But the beautiful part, I think, about the learning approach is that you're representing dynamic information, right? Because you're looking at cost paths to get from sampled states in your configuration. So what's important might change based on what area you are in your state space. So this has the ability to represent dynamic information from your scenarios, which can be particularly important because it's really for large state spaces, because it's really hard to anticipate every region of state space. Does that make sense? All right. So that was the last slide. I forgot I had that slide. That's all I had to say. And I will see you all on Thursday. Please do not hesitate to reach out if you have any questions, and I'll be in my lab. You're welcome to come by if you have some questions, office hours wise. Okay? All right. So I'll see you all on Thursday.